Hey, chemistry crew, Mr. Collier here, and in this video we're going to talk about acid-base titrations and how we do them, what they are, and what you need to know. So an acid-base titration is a carefully controlled neutralization reaction. So it's just us doing a neutralization reaction in the lab where we're trying to neutralize an acid or a base, meaning we're reacting an acid with a base to make something neutral. And what it allows us to do is figure out the concentration of an unknown. It could be an unknown acid, it could be an unknown base, but we want to determine what the strength of that unknown is. To do this, we need a standard solution. The standard solution is either an acid or a base that has a known concentration. So if we're going to neutralize something, we're basically going to say, here's this thing I don't know how strong it is. Here's this thing I do know how strong it is. And by combining them until I have something neutral, I can calculate how strong the unknown was. We can also graph this on something called a titration curve, which shows how the pH changes during a titration. So the first thing we need is an indicator. Typically, it's going to be phenolphthalein in a titration, but you certainly could use other things. Phenolphthalein is nice because it turns that nice pink color when you have a base. Now, the point where you have enough standard solution to be perfectly neutral is called the equivalence point, right? When you have a perfectly neutral solution, they are equivalent, right? The acid and the base, and so we call that the equivalence point. Now, the point at which the indicator changes, right? If it turns pink, then that's no longer perfectly equivalent. That's called the endpoint. But what we're trying to do in a titration is we're trying to add it slow enough that we can tell that it's just starting to turn pink, but we've added so little that we can kind of just call the equivalence point and the endpoint the same thing. So how does this work? So here in this example, we have a solution of sodium hydroxide. That is something we often use to unclog drains. We notice that a 43 milliliter solution of sodium hydroxide was titrated with 32 milliliters of 0.1 molar hydrochloric acid, and we want to know the molarity of the sodium hydroxide. Okay, so before we get deep into the math here, you can tell that the general idea is we took a known solution, 0.1 molar hydrochloric acid, and we mixed it with sodium hydroxide, a base, until it was neutral. We had different amounts. So if you just think for a second, if you had exactly the same amount of acid and base, right, say 43 mils of both, that would tell you that they were the same concentration, assuming it was the same values in the balanced equation of each, the same number of moles. So let's actually now look at this. So the first thing you need is a balanced equation. Here's hydrochloric acid and sodium hydroxide. Now the nice thing about this is it is a 1-to-1 ratio, right? Hydrochloric and sodium hydroxide are in 1-to-1 in this balanced equation. So the next is we need to figure out the stoichiometry to get a mole ratio, right? We want to know the number of moles of each of these chemicals to each other. So we convert from milliliters to liters, and then we use that concentration, right? When we say something is 0.1 molar, right, hydrochloric acid, that's 0.1 moles per liter. We know how many liters we just used. It was 32 mils, which is 0.032 liters. And we know the mole ratio from the balanced equation. That tells us that we used 0.0032 moles of sodium hydroxide. And if we have 0.0032 moles and we know how many liters, we can actually figure out the molarity, right? So the calculations here are not super complicated, but we are throwing a variety of different conversions at you. So just to kind of summarize, we're saying we know the volumes of these things that neutralized, but now we want to figure out what their mole ratios are so we can figure out the number of moles of the unknown that we used so that we can put that over the number of liters of the unknown we used to figure out the concentration of the unknown. Let's do one more. So here we have 25 mils of 0.12 molar sulfuric acid, a known volume of a known concentration. that neutralizes 40 mils of sodium hydroxide, an unknown, right? So let's balance this equation. And when we balance this one, and this is important, it's not 1-to-1, right? So this neutralization reaction is 2-to-1. You need 2 moles of sodium hydroxide for 1 mole of sulfuric acid. So even though the volumes might look close to each other, perhaps it's not really as close as it looks. So step 1 is going to say, well, if I had 0.2 liters, sorry, 0.025 liters of sulfuric acid, how many moles of that was there? Well, there's 0.12 moles for every liter. That would tell me, if I just did this portion of the calculation, that would tell me how many moles of sulfuric acid were in this amount of solution, this 0.25 liters, this 25 mils. But I don't really care how many moles of that. That's a means to an end. What I really want to know is how many moles of the unknown. So that's where the second value comes in. This is my conversion from moles of sulfuric acid, the thing I knew about, converting that to the moles of the sodium hydroxide, the thing I don't know about. And I know that it's 2 moles of the sodium hydroxide for every 1 mole of the sulfuric acid. That then tells me how many moles of sodium hydroxide it took to neutralize it. Once I know that, I just need to divide that number of moles divided by the number of liters of it I used. So 40 mils is 0.04 liters. And I can calculate the concentration, the molarity, the number of moles per liter of the unknown. So that's it for titrations and how you calculate them. Let me know if you have any questions, and good luck.